example, determine whether the series converge. We'll do a couple of examples. First example is we start with infinite series sine of 1 over n, 1 to infinity, and somehow we want to compare it, want to limit compare it with the harmonic series. So we want to determine the information about the series sine of 1 over n, and want to know whenever that series is convergent or divergent. So what we try to do is we'll try to LCT with 1 over n. So first we want to figure out whenever we have permission to do that. So we want to take limit then approaching infinity. We take the first one, sine of 1 over n, and we take the term of the second series, 1 over n. So what we want to do is we want to switch to corresponding functions. And sine of 1 over x divided by 1 over x. So we're going to get 0 over 0 because 1 over x is 1 over infinity is 0, so sine of 0 is 0. So we are allowed to do LHR. Limit as x approaching infinity. Derivative of 1 over x is negative 1 over x squared. Derivative of sine is cosine. Derivative of 1 over x is negative 1 over x squared. So negative 1 over x squared and negative 1 over x squared cancels out. Substituting infinity for x, we're going to get cosine of 1 divided by infinity. So we're going to get cosine of 0, we're going to get 1. So our original series, sine of 1 over n, and from 1 to infinity, and the new series, harmonic series, we are allowed to do LCT between them. We're allowed to do because limit of ratio of terms equals to 1. So look at the second series. That is harmonic series, and we know harmonic series divergent. Diverges. So by LCT, the original series do the same. So original series sine of 1 over n is divergent by LCT. That's the conclusion for the first problem. Let's try to do one more. Second one. We have series 1 minus cosine of 1 over n, and from 1 to infinity. Same question, we want to figure out whenever it is convergent or divergent. So in the previous case, we compared our given series with harmonic. Here, I'm going to compare it with some generic P series, 1 over n to p. Okay. I want to compare them. So I take a limit. And approaching infinity, 1 minus cosine of 1 over n divided by 1 over n to p. So we're going to get switch to functions, 1 minus cosine of 1 over x, and I'm going to write down that as x to a negative p. So I'm assuming that p is positive, so assuming on the bottom I'm going to get 0, and on top I'm going to get 0, because 1 minus cosine of 0 is 1, so 1 minus 1 is 0. So we're allowed to do LHR. So again, I assume that p is positive. I take limit as x approaching infinity. Derivative of 1 is 0, derivative of cosine is negative sign, so derivative of negative cosine of 1 over x is going to be sine of 1 over x multiplied by 1 over x squared with minus. And derivative of x to a negative p is going to be negative p x to a negative p minus 1. Okay, let's simplify that expression. So minus minus cancels out. So we're going to limit as x approaches infinity, sine of 1 over x. And you also notice that we can combine the powers. So we can bring that 1 over x squared down, multiplied by reciprocal. So we're going to get p times x to a negative p minus 1 times x squared. So we're going to get limit as x approaching infinity, sine of 1 over x divided by p x to a negative p plus 1. Okay. So let's assume that negative p plus 1 is still positive. So that implies that on the bottom, we're going to get 0. And sine of 0, 0. So we have 0 over 0. So we're still going to do LHR one more time. We're going to limit as x approaching infinity. Derivative of sine is cosine. Derivative of 1 over x is negative 1 over x squared times p. Negative p plus 1 going down, x to a negative p. Negative p plus 1 minus 1, so that's what it got. Okay, now we look at that expression. And that expression we want to be finite number. We want to be equals to L, and L is going to be between 0 and infinity. Okay, so let's have a look at what we got here. So we get limit as x approaching infinity, sine of 1 over x, p times negative p plus 1. I'm going to break that minus in front. And then instead of multiplying 1 over x squared on top, I'm going to multiply by its reciprocal on the bottom. So we're going to get x to a negative p plus 2. So that's what we got. We want that to be finite number. So to that to be finite number, what you notice is substituting infinity for x. Then you're going to get 1 on top, minus 1, p times negative p plus 1. And then we have x to power. For that expression to be finite, that has to be x to a 0th power. So that implies that negative p plus 2 has to be 0. That implies that p has to be 2. Okay, so we did all that. So that suggests that we have to do our original series, 1 minus cosine of 1 over n, and from 1 to infinity, and we want to LCT 1 over n squared, and from 1 to infinity. Because you remember, we wanted to compare it with 1 over n to a p, and they figure out that p has to be equals to 2. In order to get permission to do LCT, that's what we're going to get. Because that's what you're going to get. And you can do a calculation and you compare that, that L is going to be finite here. So we got permission to do LCT. And here, second series is going to be convergent. P series P equals to 2. So we turn around and we conclude that our original series is convergent by LCT and from 1 to infinity. That's a conclusion. And that's a conclusion about this example.